students. So in the yesterday's class, we discussed about the two approaches which are used to generate the codes with respect to your convolutional encoder. So in the yesterday's class, we discussed about the time domain approach, where in the time domain approach we have two methods. So one is using impulse responses and another one is by matrix method. So we have one more method which is called as the transform domain approach. So where in the case of transform domain approach, so the impulse response is what we are going to consider. So that is being converted to polynomials. Okay. So now, as we already know that we have a generator polynomial. So in general, when we are using transform domain approach, so the generator polynomial or the generator matrix, it is represented as j of x, where j varies from 1 to n. J varies from 1 to n. So where j is nothing but the number of outputs what we have. So we have this equation, that is g1 of j, g2 of j into x. So this continues up to gm plus 1 of x into x to the power of m. So now we need to represent the output of each of the adders. That means if we consider the example here, so where you can see here we have two adders, that is C of 1 and C of 2. So this is nothing but these are the two adders what we have, where we call it as the top adder and the bottom adder. So depending upon the adders what we have, we are going to consider those outputs. So if we consider the adders, the output of each adder, then in general it is represented as Cj of x is equal to d of x into g of x. That means we are going to generate the codes by multiplying with respect to the message input as well as the generator polynomial, that is g of x. And then we are going to find the final output of the encoder, that is C of x, by considering both the adders output, that is C of 1 into x power n plus x into C of 2 into x to the power of n, plus that continues. So that depends upon how many number of outputs we have. So this is how we are going to represent in general your transform domain approach by considering their polynomials. So now how this is taken or how this is used to solve the problem is done with the by taking with the help of an example here. So we have the diagram which is shown has 3 modulo adders and 2 outputs and 1 input what we are inputting at a particular instant of time. So now what we need to find? We need to find what is your generator polynomial, that is with respect to the 2 adders. So since we have 2 adders, so we are going to find g1 of x. So g1 of x is, so as previously mentioned, so wherever we get a connection with respect to the adder, we are going to consider it as 1. So it is 1, so it is 0, then 1 and 1. So where I can write this as x, so that means, so this power is 0, 1, 2 and 3. So it is x to the power of 0 means it is 1 plus, so it is x is 0, it is x square plus x to the power of 3. Okay. Next we have g2 of x. So g2 of x is all 1, since we have all the connections with respect to your flip-flops. That means the output of the flip-flops are all connected to the adder, that is C of 2. So then it will be 1 plus x square plus x to the power of 3. Okay. So now we need to find C of x, is d of x into g of x. So let us consider your d of x is equal to 1 plus x square plus x to the power of 3 plus x to the power of 4, which is nothing but it is 1, 0, 1, 1 and 1. Okay. So this is d of x So whatever we are going to consider, so everything has to be represented in terms of its polynomial. So now once we have found out g of x and d of x, so finally we need to find what is your c of x. So how we are going to find your c of x is, you are going to use this formula to calculate your c of x. So that means, so first you are going to find c1 of x. So c1 of x is equal to d of x is what? So it is 1 plus x square plus x to the power of 3 plus x to the power of 4 multiplied by your gj of x means it is g1 of x. So I can write this as d of x into g1 of x. So g1 of x means it is multiplied by 1 plus x square plus x to the power of 3. Okay. So now we are going to multiply this. So it is 1 plus x square x3 x4 plus x square plus we have x to the power of 4 plus x to the power of 5 plus x to the power of 6 plus x to the power of 3 plus x to the power of 5 plus 6 plus 7. So since we are performing the XOR operation here, what we need to do here, so wherever we have the similar exponential, that is we have x square and x square, so that is considered as 1 plus 1. So you know that 1 plus 1 is 0. So that we are not going to consider here. So we have x to the power of 4 and x to the power of 4, x5 and x5, x3 and x3, x6 and x6. So we get 1 plus x to the power of 7. So this is how we are going to calculate what is c1 of x. So now we need to find what is your c2 of x. So let us find c2 of x. So where c2 of x is equal to d of x into g2 of x. So d of x is 1 plus x square plus x to the power of 3 plus x to the power of 4 into g2 of x is 1 plus x square plus x to the power of 3. Okay. So now if we simplify this, we are going to get x to the power of 4 plus x to the power of 3, 4 and 5 plus x square 4, 5, 6 plus x to the power of 3 plus 5 plus 6 plus 7. Okay. So now further simplification, so x square and x square, x3 and x3, x4 and x4, x5 and x5. Then we have x6 as well as x6. So we get 1 plus x to the power of 3 plus x to the power of 4, 5 and 7. Okay. So now what we need to find? We need to find what is the total output, that is c of x. So we need to consider c of x as c1 into x to the power of 1. So c of 1 into x to the power of n. N means the number of outputs what we have. So as we have seen in the diagram, so we have two outputs, so n is equal to 2, that is c of 1 into x square. That means we are going to multiply by 2, whatever the powers we have, that gets multiplied by 2. So the first is x square with respect to c1 of x, so it is 1 plus x square means it is x to the power of 14. Then we have c2 of x to the power of n. So this is your c of 2, that is c2. So it is 1 plus x square 6, 8, 10 and 14. So finally we need to write what is your c of x. So C of x is equal to C1 into x power n. What is C of? So it is 1 plus x to the power of 14 plus we have one extra polynomial which has to be multiplied with respect to C of 2. So it is x into 1 plus x square plus x6 plus x8 plus x10 plus x14. So this will be equal to x plus 3, 7, 9, 11 and 15. So we get x plus x to the power of 3, 7, 9, 11 plus 15. So now considering the above equation what we get, so wherever we have the polynomials present we are going to consider it as 1 and wherever we do not have the polynomials we are considering it as 0. So that means, so it is x to the power of 0 means it is 1, so we have 1. So we do not have 1 plus x to the power of 1, so we have 0. So x square is also 0, x to 1, so we have x here, so it is also 1. X square we do not have, so it is 0. X power 3 is there, x power 4, 5, 6, 7, 8, we have 9, 10 is 0, 11, so we have 12, 13, then we have 14 and 15. So how many bits we should have? So we have 16 bits. So they are paired together. Okay. So if we compare the codes what we have got from the transform domain approach with your time domain approach, you are going to get the same code words. So this is how we are going to find the code words by using the transform domain approach. So now let us solve a simple example, one more example by using either time domain approach as well as transform domain approach. So where the problem given as consider the 312 convolutional code with G of 1, G of 2 and G of 3 with the message input which is given. So we need to find the convolutional codes either by using time domain approach or transform domain approach, and we need to verify whether we are going to get the same codes when we use either of those methods. So now since they have not given the diagram here, so we need to first write the diagram with the data which is given here. So we have 312. So 312 is what? It is N, K and M. That means we have 2 modulo adders. That means we have 2 flip-flops which is given. Okay. And then we have 3 outputs. So 3 represents the 3 outputs here. So now if we consider G of 1. So G of 1 means, so we have the connection with respect to the first one as well as with respect to the from the second one. So I can write this as your C of 1. Next we have G of 2 which is 101. It is nothing but the middle adder. So we have the connection with respect to this is 1. Okay. And the output of this. So this is your C of 2. Next we have G3. So it is, we have 1 as well as, okay. So this is your C of 3. So now, so this is given to your channel output. So all of them are connected to your channel. Okay. So this is how you need to construct the encoder diagram by the data which is given. So now let us find first with respect to the time domain approach. So in the time domain approach, so I am considering here the matrix method. So when we are going to consider the matrix method, so we need to know first what is your generator polynomial, okay, that is G. So in order to find your G, the generator polynomial, you should know first what is the size of the matrix. So the size of the matrix is calculated with the help of the formula, that is L into N into L plus M. So L represents the length of the message code. What is the length of the message code? It is 5 cross. So N means it is 3. So 3 into L plus M means it is 5 plus 2, that means it is 7. So that means you are going to get 5 cross 21. So that is the size of your matrix is 5 cross 31. So now in order to construct this matrix, that means we have 5 rows and 21 columns. So we need to consider all the 3 generator impulse responses here. So if we consider these 3, so we need to consider the first bit of G1 and the second bit of G of 2 and the third bit of G of 3 next. So we have next bit is 1, the second bit it is 0, and from here it is 1, then the third bit is 0, 1 and 1. So now what should we have to do with respect to the next bits here? So it is replaced by zeros. So now, so we have 9 bits, and rest of what we should get is, we should get 21 columns. So rest of the bits, so that is represented by zeros. So now fill this generator polynomial. Triple 1, 101, 0, double 1, 0, 0, 0, 0, 0. One zero one 0 1 1 0 0 0. One zero one 0 1 1. So this is how we are going to construct the generator matrix. So now what we need to find? So we need to find what is your code word C. So C is equal to D into G. That means this matrix has to be multiplied with the message input, that is 1 1 0 1. So multiplied by your G. So G is nothing but this one. So you are going to get, when you multiply D with your G, so as I have already indicated how to multiply your G with your D. So this is the result what we are going to get with respect to your matrix method. So let us solve the same problem by using your transform domain approach. So for solving with respect to the transform domain approach, the impulse responses has to be replaced by its polynomial. So we have G1. So G1 is taken as 1 plus x, then G of 2 is 1 plus x square, then G of 3 as 1 plus x square. So similarly, so your D is represented as D of x is equal to 1 plus x square plus x to the power of 4. Okay. So now first what we need to find? So we need to find, so what is your code with respect to your C of 1? That means we have 3 outputs. So we need to find what is your C1 of x. So C1 of x means it is D of x into G1, D of x into G1 of x. So it is 1 plus x square plus x to the power of 4 multiplied by 1 plus x. So, it is 1 plus x square plus x to the power of 4 x square x3 plus x5. So, now if you apply the XOR operation here, so you are going to get 1 plus x to the power of 3 x to the power of 4 plus x to the power of 5. Now, similarly we need to find what is your C2 of x. So, C2 of x is 1 plus x square x to the power of 4 into G2 of x. So, it is 1 plus x square. So, you are going to get 1 plus x square x to the power of 4 x square x3 x4 plus x6. Okay. So, next similarly we need to find what is your C3 of x. So, it is 1 plus x square, that is nothing but your d of x into G3 of x. So, it is 1 plus x square. So, you are going to get 1 plus x square plus x to the power of 4 plus x square x to the power of 3 x to the power of 5 plus x square plus x3 x4 plus x6. So, now if we simplify this, x square and x square, x4 and x4. So, you are going to get 1 plus x to the power of 3 plus x to the power of 6. So, if we consider this, so we are going to get x and x get cancelled, x square x to the power of 4 and x to the power of 4, x to the power of 3 and x to the power of 3. So, we have 1 plus. So, this we are going to get as, so we got C3 of x also. So, your C1 of x is 1 plus x to the power of 3 plus x to the power of 4 plus x to the power of 5, and your C2 of x, after simplification we get 1 plus x to the power of 3 plus x to the power of 6, and similarly your C3 of x is 1 plus x to the power of 5, x power is 2, x to the power of 5 plus x to the power of 6. Okay. So, now we need to combine all these together to get your C of x. So, C1 of x, so that C1 of x to the power of n. So, what is n here? N is equal to 3. So, that means it is x to the power of 3. So, it is 1 into x to the power of 9 plus 3 into 4 is 12 x to the power of 15. So, similarly, so it is x into C2 of x to the power of 3. So, we are going to get x multiplied by 1 plus x to the power of 3, 9 plus 18. So, further we are going to get as x plus 4 plus 10 plus 19. So, next we have x square into C3 of x to the power of 3. So, it is x square multiplied by 1 plus x to the power of 6, 15 plus 18. So, you are going to get x square plus 8 plus 17 plus 20. Okay. So, now we have to write what is your C of x. So, C of x is equal to, so we have C1 1 plus x power 9, x power 12, x power 15 plus x power 4 plus 10 plus 19 plus x square plus x8, x17 plus x20. So now from this you need to check whether any of the terms are repeated. So here x, so we don't have any of the terms which are repeated. So now, so we have x here, it is 1, so we have 1, so we have x, so it is 1, x square, we have 1, we don't have x3, x4, x5, x6, x7, okay, then x8, x9, x10, x11, 12 is there, 13, 14, 15, 16, 17, 18, 19, then we have 20. Okay. So now if you group them in terms of 3, 3. So now compare the answer with the transform domain to the time domain approach what we have got. So it is 111. So this and this gets verified. 010, 010, 001, 001. So it is 110, 110, 100, 100, 101, 101, 011, 011. Okay. So this is how we are going to solve the problem with respect to the two approaches with respect to your convolutional encoder. So now the problem can be asked either by giving a block diagram or without a block diagram. So if suppose they give you the block diagram, you need to find what are the generator polynomials or the generator sequences, as well as the message input will be given in both the cases, and in the first case you will be given a block diagram, and from that you are going to find the G values and you are going to simplify the problem. In the second way, so they can just give you the data, that is they can give you the generator sequences. You need to represent the given data with the help of a block diagram, and from the block diagram, after representing it in the block diagram, you are going to solve the problem further. Okay, good morning students. So let us discuss about the next topic what we have with respect to the convolutional encoder. So which is called as the state diagram, that is the state diagram representation of the convolutional codes. So whenever we are going to represent the convolution codes using state diagram, so we need to follow some process or we need to follow some stepwise procedure here. So by using the state diagram, we are also going to represent the state representation in the form of a code tree, where we call it as a tree diagram. So first we will see how we are going to represent the state diagram, and in the further classes we will study about how we are going to transform the state diagram to a code tree. So now, so this is the diagram which is given. So where you can see we have two flip-flops and two modular adders. That means to say we have two outputs, that is C1 and C2. So now with respect to this, so before we construct a state diagram, so we already know that state diagram is nothing but a graphical representation of the different states. Okay. So where we are going to use the circles to represent the states, and that means if we have from one state to another state transition, so that is represented by a directed line. So the first three steps what we have with respect to the state diagram is we need to first construct a state table. So state table is going to tell you how many number of states we have with respect to that particular state diagram. So now looking into the block diagram what they have given, so depending upon the number of flip-flops, so we are going to represent these states. That means if we have 3 flip-flops, it will be 2 to the, that means 2 to the power of n states. That means to say that, so n represents the number of outputs. So we have 2 outputs, so we have 2 to the power of 2, that means we have 4 states. Okay. So 4 state means, so it is S0, S1, S2 and S3. So whenever we are going to write the states, so we are representing S0 by 0, 0, but when we represent S1 or any other codes, so S1 is usually represented as 0, 1, but in the case of representation of the state diagram, we are considering from reverse order, that is 1, 0. Similarly, so it is 1, 0 is S2 is 1, 0, but we are going to represent it as 0, 1. So 1 and 1 is 1 and 1, 1. So we have 1, 0, 0, 1 and 1, 1. Okay. So suppose if we have 2 to the power of 3, that means 8 states. So for that also you need to apply this. That means you have to reverse the code, and those reversed codes will be represented in the state table. So where this is your states and this is your binary description of that particular state, that is S0, the binary description of that is 0, 0. So now once you represent the states in the state table, so the next step is you need to write the state transition table. That means how it is going to change its states from the initial state to the next state, how it is done. So it is done here is with respect to a state transition table. So where this state transition table is constructed in this way, so where PS is nothing but the present state. That is, we have 4 states, it is S0, S1, S2 and S3. So these are the present states, and corresponding to the present states we have written the binary description of those. Then depending upon the input, it is going to shift to the next state. So suppose if the input is 0, so what is the next state? And suppose if the input is 1, what is its next state? Similarly, the binary description of the next state. Then DL, DL minus 1 and DL minus 2 are the inputs what we are going to apply with respect to the encoder diagram, and C of 1 and C of 2 are the outputs what we are going to do. So here also we are going to perform the XOR operation. So now what is C of 1 and C of 2? So that is calculated from the diagram here. So where we have a connection from the input to the top adder, so that is represents DL. Then we have output from the flip-flop 1, so it is DL minus 1 plus the third output, that is DL minus 2. Then C of 2 is DL, so we don't have a connection to this adder, so it is DL minus 1 is 0, but we have DL minus 2. That means when you are going to calculate the output C of 1 and C of 2, you need to consider these 3 bits, that is DL plus DL minus 1 plus DL minus 2 for C of 1, and C of 2 DL plus DL minus 2. Okay. So now let us see how we have written this state transition table. So for the present state S0, if it is 0, 0, and if the input is 0, that means the flip-flop contents for the present statements, the flip-flop contents are 0, 0 for S0 state, and we are considering the input to be 0. So in this condition what happens? So the next state will also be your 0, 0 only. That means we don't have any changes here. So your state of the flip-flop is S0 itself. So what about the contents of DL, DL minus 1 and DL minus 2? So this is your DL, so it is 0. This is DL minus 1 and this is DL minus 2. So this is DL, DL minus 1 and this is your DL minus 2. So we get all zeros. So output is also 0, 0 with respect to C1 and C2. Next, so when the input gets changed to 1, so input gets changed to 1, but the flip-flop states it is 0, 0 only, because we are considering first the present state and then only we are going to consider the next state. So in that condition what happens? So when you input 1, so previously it was 0, 0. So now when you are applying 1, the flip-flop contents, since these are the shift registers, so it is going to shift the present bit to the next register. So that means the flip-flop contents now gets changed to 1 and 0. So previously it was 0, 0, now it is 1, 0. So that's why we have written 1, 0. Then the contents of your DL, DL minus 1 and DL minus 2 will be, so this is 1, what is the outputted bit which is going to flip-flop to when it is shifted, so it is 0. So that we need to consider here with respect to this particular adder. So that's why you will be getting 1 0 0. So now if you add these three, 1 plus 0 plus 0, XOR 1 XOR with 0, XOR with 0 is 1. Similarly, 1 XOR with 0 is also 1. So this is how you are going to complete the whole state transition table by considering the present state, the next state, as well as the conditions for calculating the output, that is C of 1 and C of 2. So now looking into the state transition table, so now let us write the state diagram. Okay. So now let us write the state diagram with respect to the state transition table what we have. So what are the 4 states we have? We have S0, then we have S1, we have S2 and we have S3. So these are the 3 states what we have, 4 states what we have. So S0. So for S0, so when the input is 0, what is the next state? It is 0. Okay. So that means it is going to remain in the S0 state only. So for what? For the input 0. Okay. For the input 0, what is the output? C of 1 and C of 2. So it is 0 0. So now when you input 1, so what is the next state? So when you input 1, what is the next state? So the next state is S1. So that means it make a transition from S0 to S1 when the inputs gets changed from 0 to 1. So for input 1, the output is 1 1. Next. So if we consider for S1 state, so with respect to S1 state, when the input is 0, so it makes a transition to S2. So what is its corresponding output? It is 1 0. So when the input is 1, it makes a transition to S3. So what is the corresponding output? We have 0 1. So if we consider S2 state with respect to input 0, it makes a transition to S0. With input 0, the output is 1 1. So with input 1, it makes a transition to S1. What is the output? The output is 1 0. So similarly, if we consider the state S3, so with input 0, it makes a transition to 0. It makes a transition to S2 with output 0 1. So with input 1, it makes a transition to self. With input 1, it remains in the S3 state itself, and what is its output? The output is 1 0. Okay. So this is how you are going to write the state diagram with the help of the state transition table. So now from the state diagram, we need to construct the code tree. So this code tree part we will continue in the next class. Thank you.